Take it away. Okay, so good afternoon, everybody, and thank you very much for the introduction. It's a great pleasure to be here. So today I'm going to talk about sum of squares of positive eigenvalues. So everything that I will talk about is joint work with Gabriel Coutinho from the Federal University of Minas Gerais and Sheng-Tong Zhang from Stanford University. Okay, so just to give some motivation, let's see what is Turan's inequality. Okay, so let's say I have a graph G with n vertices, m edges, and clique number omega. Then result by Turan from 1941 says that the number of edges of the graph G is maximized for the Turan graph. The Turan graph for Tn omega. So what is this Turan graph? So it is the complete multipartite graph formed by partitioning the n vertices into omega sets with approximately n over omega vertices in each set. Okay, so here, for example, there is the Turan graph 14, 4 or 13, 4. Yes, 13, 4. Okay, so how many edges there are in the Turan graph? So in the Turan graph, we get essentially this upper bound right here for the number of edges. And we can write in this form. So it's this fraction of the total possible number of edges. Okay? So I will refer in this talk to Turan's inequality, meaning this inequality right here, that 2 times the number of edges of the graph is at most this quantity right here involving the number of vertices and the clique number. Okay? So we also have a spectral version of Turan's inequality, which is called Wilks inequality. So just to state this inequality here, we consider a graph G with n vertices, m edges, and clique number omega. And let's say the eigenvalues of the adjacency matrix are lambda n to lambda 1. Lambda 1 is the largest one. Then Wilks inequality says that the largest eigenvalue is at most this quantity right here. Okay? And this inequality by Wilk is stronger than Turan's inequality. And this is because there is this lower bound for the maximum, for the largest eigenvalue of a graph, where we just use the min-max characterization of the eigenvalues and we plug in the all-ones vector, okay? So the largest eigenvalue of the graph is always at least 2 times the number of edges divided by n. Okay, so using this, we can see that Wilks inequality implies Turan's inequality. Okay, but there is also a stronger inequality by Nikiforov, which says that the largest eigenvalue of the graph squared is at most this quantity right here. And you can see by using the same inequality, the same lower bound for the largest eigenvalue of the graph, you can see that Nikiforov's inequality implies Wilks inequality that implies Turan's inequality. Okay, so we are going to be working with generalizations of Nikiforov's inequality and inequalities associated with this one. So first, let me give you an idea of how the proof goes for Nikiforov's inequality, okay? So the proof of Nikiforov's inequality. In order for me to give you the proof, I need to define this concept of the inner product between 2 real symmetric square matrices. So for 2 real symmetric square matrices, X and Y, I define this inner product, the trace inner product, which is simply defined as the trace of X times Y. Okay? Usually there is a conjugate here, but since we are working with real symmetric matrices, we don't need the conjugate transpose. And okay, so this is the definition. And then we know that this is equal to the sum of the entries of this matrix right here, which is X Hadamard product with Y. The Hadamard product is the matrix we obtain by multiplying entry-wise the 2 matrices. Okay, so we get this equality right here for the trace inner product. It can be written in this way. Okay, so this is the trace inner, the Frobenius inner product or trace inner product. And let me give you some properties of this Frobenius inner product. So, for example, when we take the matrix X and we compute this inner product with a rank 1 matrix, we obtain this right here. Okay. let's say I have the matrix X, we have the spectral decomposition of the matrix X, and we compute the inner product with one of the projectors, and we get the eigenvalue, for example. And if we take the inner product with of a matrix with itself, we get the sum of the squares of the eigenvalues. Okay, so these are just some of the properties of the Frobenius inner product. Some other things you can check is that if you have two PSD matrices and you compute the inner product, you get something that is non-negative. And if the matrices are non-negative, you also get something that is non-negative, okay? And if I put the inner product of X with the all ones matrix, I get simply the sum of all the entries in the matrix X, okay? Okay, so using this is the first ingredient of the proof of Nikiforov's inequality. And the second ingredient is the Motzkin-Strauss inequality, okay? So here in the Motzkin-Strauss inequality, we consider the simplex formed by the probability vectors. And the Motzkin-Strauss inequality says that this right here, when we take the maximum over the simplex, is exactly 1 minus 1 over the clique number, okay? And there is equality if you take the characteristic vector of maximum clique. Okay, so this is the Motzkin-Strauss inequality.
So A is the adjacency matrix?
What? Sorry?
What is A there? A is the adjacency matrix?
A is the adjacency matrix, yes. And we can rewrite the Motzkin-Strauss inequality in this way. So here we have the inner product of the adjacency matrix with a rank 1 matrix given by this vector V. This vector V is non-negative. This corresponds to this right here. And here we have this projector inner product with the all ones matrix. Okay, so this is just rewriting the Motzkin-Strauss inequality in this form right here, using the trace inner product that I defined to you. Okay, so you can see by linearity that this inequality holds true for any matrix that can be written as a sum of matrices formed by vectors of satisfying that they are non-negative, okay? So I can rewrite the Motzkin-Strauss inequality as saying that the inner product of the adjacency matrix with X is at most this right here, where now X is a completely positive matrix, okay? So it's we call a matrix that can be written in this form as a completely positive matrix. Okay, so using the Motzkin-Strauss inequality, we can see, for example, how to prove trans inequality. So, for example, here we have the Motzkin-Strauss inequality, and we just plug in for the matrix X the all ones matrix. Then we get here the sum of the entries of the adjacency matrix, which is just 2 times the number of edges. And here we get n squared, which is just the sum of the entries of the all ones matrix. Okay? So this is Turan's inequality. And okay, and how can we prove Nikiforov's inequality? So first we just do some rearranging. So we see that we can get the largest eigenvalue of the graph just taking the inner product of the adjacency matrix with the first projector. So we take the squares in here, and just by using this manipulation, using the Hadamard product, noticing that the Hadamard product of a 0, 1 matrix with itself is equal to the matrix, we can write in this way right here, okay? So the largest eigenvalue of the graph squared is exactly this right here. And now we apply Cauchy-Schwarz. So we just apply Cauchy-Schwarz inequality right here. Here we have an inner product, so we can apply Cauchy-Schwarz. So we get A inner product A, and this other thing right here. And okay, so this is equal, A inner product A is 2 times the number of edges. And this other thing right here, we can rewrite in this form. And now we can see that we can apply the Motzkin-Strauss inequality on this thing right here. And when we apply the Motzkin-Strauss inequality, we get this right here. And this last term is simply 1, because V is a normalized eigenvector, and yeah. And so we get what we wanted, which is this right here. But, okay, if you didn't got the details, it's okay. The main takeaway here, it's this procedure of just taking the, applying the Cauchy-Schwarz inequality, and then the Motzkin-Strauss inequality, okay? This is what we are going to be using. Okay, so we have Nikiforov's inequality, and then we have the 2 other related inequalities, which is what I am going to talk to you about today. So the first one is Bockschen-Elphig-Anechstein's conjecture from 2018, and it says that if we instead of considering only the square of the largest eigenvalue of the graph, we consider the sum of the squares of the positive eigenvalues of the graph, then we get this upper bound right here, where instead of the clique number, we have the vector chromatic number. I will define what is the vector chromatic number, okay? And the other inequality related to this first one is the Bolobaj-Nikiforov's conjecture. And this says that if we exclude complete graphs, because basically complete graphs are the equality case right here for the first inequality, then we can insert another term corresponding to the square of the second eigenvalue of the graph. So here you can see that there is this, it's the same upper bound as in Nikiforov's inequality, but now I have 2 eigenvalues. Okay? And I am going to talk about these 2 inequalities. Okay. And another motivation for this, instead of Turan's inequality, well, we know that the sum of the squares of the eigenvalues of a graph is always equal to 2 times the number of edges. And the question is, what factor we can save if we sum only the top eigenvalues, the squares of the top eigenvalues of the graph? Okay, so this is another motivation for this conjecture. Okay, so first this one, Bockschen-Elphig-Anechstein's conjecture. Okay, so first I will talk about Bockschen-Elphig's conjecture, where instead of the vector chromatic number, there is the chromatic number of the graph. So let chi be the chromatic number of the graph. Notice that the clique number is always at most chi. And denote by S plus and minus the sum of the squares of the positive and negative eigenvalues of G. So by what I said before, the sum of these 2 quantities is 2 times the number of edges, okay? Here is just the definition. So Bockschen and Elphig conjectured in 2013 that the sum of the squares of the positive eigenvalues of the graph is always upper bounded by this quantity right here, where here is the chromatic number. And this was proved by Andu and Lin in 2015, okay? After that, they conjectured the stronger inequality using the vector chromatic number after the proof of Andu and Lin. So the vector chromatic number of a graph G is the smallest alpha, so that we can assign unit vectors to the vertices of the graph, such that for each edge, the vectors of the corresponding vertices satisfy this inequality right here. So they must be in an angle that is bigger than pi over 2. Okay? So we have that the vector chromatic number sits between the clique number and the chromatic number. And we actually know that the vector chromatic number can be computed in polynomial time. Okay? And the conjecture was this one, that we have this upper bound for the sum of the squares of the positive and negative eigenvalues of the graph. There was partial progress towards this conjecture by Guo and Spier in 2022, where instead of proving for the vector chromatic number, they proved for the fractional chromatic number that sits between the vector chromatic number and the chromatic number. Okay? And the proof of this result uses homomorphisms to edge transitive graphs and ideas motivated by association schemes. But what we will see doesn't use anything like that. Okay? And then we actually proved the conjecture with the vector chromatic number, so the correct conjectured bound. So let's see the proof of this result right here. Okay, so how the proof goes. So first, we write the adjacency matrix of the graph as the difference of these two PSD matrices. A plus is simply the sum of the projectors, this sum corresponding to the positive eigenvalues of the graph, and A minus is the analogous sum for the negative eigenvalues of the graph. Okay, so you can check that the inner product of the adjacency matrix with A plus is exactly equal to this to the sum of the squares of the positive eigenvalues of the graph. And since the matrices A plus and A minus, they are orthogonal with respect to this inner product, this is also equal to A plus inner product with A plus. Okay. Okay, so now what we do? By Cauchy-Schwarz inequality, we can consider this inner product right here of the adjacency matrix with this matrix A plus. So we apply Cauchy-Schwarz, we get this right here. And note that if this matrix A plus, sure, A plus were completely positive, then by the Motzkin-Strauss inequality, we would get this inequality right here. Okay? This inequality right here, and here I'm just rewriting. Okay? And if we combine these two inequalities, then we get the inequality that we want, which is just that the sum of the squares of the positive eigenvalues of the graph is upper bounded by this right here. Okay, so if we just combine Cauchy-Schwarz with Motzkin-Strauss, we get what we want in this case as well. But the problem is that in this matrix A plus, sure, A plus Hadamard product with A plus is not completely positive in general. So we cannot do this, okay? But well, we don't want to prove the inequality with the clique number right here. We want only the inequality of, yes.
Okay, what do you mean by completely positive?
Completely positive, it's the sum of, okay, ready? If it can be written in this way, okay? The vectors in the sum, they are all non-negative. Okay? Yeah, so this matrix need not be completely positive in general, so, but it's fine. I mean, we just want to prove this inequality right here with the vector chromatic number. So if we prove this, then by the same reasoning, well, now we get this upper bound, which is what we want. So let's prove this inequality right here. Simply this inequality right here. Notice that in order to prove this inequality, it suffices to prove that this right here holds for every matrix Z, which is PSD and non-negative, okay? Because this matrix A plus, Hadamard product with A plus, satisfies these two properties. It is PSD by the Schur product theorem, and it is non-negative because, well, the entries of this matrix are all squared, okay? So it certainly satisfies these two conditions right here. These two conditions are named doubly non-negative, okay? Matrix that satisfies these two conditions. Okay, so we want to prove this inequality right here. For every matrix, for every doubly non-negative matrix. So just by rewriting, we can write this in this form right here. So, and then you can see that it suffices to prove that the vector chromatic number is actually given by the maximum of this program right here, okay? The maximum of J inner product with the matrix Z, subject to these conditions right here, right? But when you look in the literature, you can see that the vector chromatic number is actually given by the second program right here, okay? Which is close to the first one, but not equal, okay? Because here, well, you have this extra condition right here. right? But we can prove that the optimum of these two programs are actually equal, so that the vector chromatic number is also the optimum of the first program, okay? And how do we do this? You can notice that every feasible solution to the program 2 is a feasible solution for the first program. So that, of course, the maximum of the first program is at least the maximum of the second program. The converse doesn't hold, so not every feasible solution in the first is a feasible solution to the second. But what we can do is that we can take an optimum of the first and transform in a feasible solution for the second program with the same value, okay? And how do we do this? We simply use this transformation right here that works in this case. So we sum a bunch of matrices for the optimal solution of one, and this turns out to be a feasible solution for the second program with the same objective value. Okay, so using this, we can prove that both programs have the same optimum value given by the vector chromatic number, and this proves the first conjecture. Okay. Okay, so what we can get from this conjecture, we have two other observations that I think are worth saying. So the first one is that, again, if we have Buff's inequality right here, and we square it, we get this other inequality right here. And Elphick and Boxian's conjecture that the sum of the squares of the positive eigenvalues of the graph is upper bounded by this quantity right here. Okay, it's just the same right here. We can insert all the squares of all the positive eigenvalues of the graph in this first inequality. And using our results together with Turan's inequality, we can get some partial progress towards this inequality right here. So this is just by using our upper bound and then applying Turan's inequality. So we get this right here, but the conjecture remains open, okay? And another observation is that we get this sort of Cauchy-Schwarz inequality when we have some information about the support of the entries of the Hadamard product of two matrices, okay? So let's say here we have a matrix, a PSD matrix X, and Y is a symmetric matrix with zero diagonal. Let's say A now is a 0-1 matrix denoting the support of the Hadamard product of X and Y. Then X inner product Y is equal to this right here. And we can get this upper bound using that the two programs were equal, yeah, using the same. Okay. Yeah, so this is all I had to say about the first conjecture. And now I am going to talk about the Bolovaj-Nikiforov's conjecture. Okay, so here the conjecture is that if G is not a complete graph, then we have this upper bound for the sum of the squares of the two largest eigenvalues of the graph. So what is the partial progress towards this conjecture? We have a result by Ning, and Wu from 2021, which proves this conjecture when the clique number is equal to 2. And they actually determine that equality holds if and only if G is a blow-up of one of these graphs right here. Then there is result by Shentong from 2023, where he proves the conjecture for regular graphs. And he determines that the equality holds if and only if G is a Turan graph or a union of two Turan graphs with the appropriate parameters. Okay? And finally, there is recent work by Kumar and Pragada from 2024, where they prove that the conjecture is true for graphs with few triangles. So here few is less than m to the 1.5. And using this in particular, they verify the conjecture for planar graphs, book-free graphs, and cycle-free graphs when the number of edges is large. Okay, so this is the partial progress towards this conjecture, and I'm going to talk about our recent work showing that we have this inequality right here, where instead of the clique number, we have the clique number times a constant. okay, and it's this funny constant right here, not 42. So it's the first bound that holds for all graphs and saves a factor over the trivial bound. And it's comparable to the conjectured bound. And I'm also, yeah, and we also have this result right here, showing that when the clique number is large, then we get a better bound, okay? So it's like, yeah. Okay, so I'm not going to give you the proof of any of these two results, but I'm going to give you the proof of a weaker inequality, which is similar to this first one right here. And this is the inequality. So if G is not a complete graph, then the sum of the squares of the largest eigenvalues of the two largest eigenvalues of the graph is at most is right here, where there is a 2 in front of the clique number. Okay, so what is the proof? So again, we consider a sum of projectors corresponding to the adjacency matrix. Here, we only consider the projectors for the two largest eigenvalues of the graph. And then we notice that the sum of the squares of the two largest eigenvalues of the graph is equal to this inner product right here of the adjacency matrix with this matrix X. And again, because X is orthogonal to A minus X, we get this other equality right here. So that we want to get an upper bound for this quantity right here, okay? So what do we do? Once again, we apply the Cauchy-Schwarz inequality. So applying the Cauchy-Schwarz inequality in this trace inner product right here, we get this. So it's 2 times the number of edges times A inner product with X Hadamard product with X. And now we notice again that if X Hadamard product with X were completely positive, then by Motzkin-Strauss inequality, we would get this inequality right here and the bound that we want, okay? But again, we don't know that X Hadamard product X is completely, if it is completely positive, and it is not completely positive in general, okay? So we cannot do that. So what do we do instead? In this case, it is good that we are not that far off from complete positivity, okay? So there is this nice fact right here that says that if you have a matrix that is PSD and non-negative, and such that the rank is upper bounded by 2, then this matrix is completely positive, okay? So doubly non-negative implies completely positive if the rank is at most 2. So why is this true? This is simply because, well, since Z is PSD, it is the Gram matrix of vectors in R2, okay? And since Z is non-negative, the angle between any two vectors is pi over 2, okay? So we could have something like, let's say here are the vectors for such that X is a Gram matrix. So we know that the angle between any two vectors is at most pi over 2. Okay? So in particular, if we take the vectors with the largest angle, well, we know it's an angle that is at most pi over 2, and every other vector needs to sit inside here, inside this region, determined by this vector with maximum angle. Okay? And then if we rotate these vectors, we can rotate these vectors to the positive quadrant. Okay? So for example, and by doing this rotation, since all the vectors are in the first quadrant, we can see that the matrix is completely positive. Okay, it's equivalent to this. This holds if and only if all the vectors such that X is a Gram matrix, they are in the first octant. They are all octant. Okay, so we have this fact that doubly non-negative is equal to completely positive if the rank is at most true. And in our situation, we can see that the matrix we are dealing with, it has rank true. And if we compute the Hadamard product, we get a matrix which is this one right here. And this matrix is certainly, it is PSD, it is non-negative. And you can see from this expression that the rank is at most 3. Okay, so we are not that far off from rank 2, the good situation. Okay, so what we can do with this information, knowing that our matrix has a small rank, this matrix X, Hadamard product with X. Okay, we are going to prove this inequality in this case, okay, where the rank is upper bounded by 3, and we have these two conditions that the matrix is PSD and it is non-negative. Okay, we are going to prove this inequality. Okay, so again, notice that we can rewrite this inequality in this form right here. So we want to prove this bound for a doubly non-negative matrix with rank at most 3. And so now what we can do, knowing that the rank is small, we notice that Z is a Gram matrix of vectors in R3, and the angle between any two vectors is at most pi over 2. Okay, by the same procedure when I was telling you about the fact. Okay, same situation as this right here, but in R3. And you can see that since we are in R3, now we can rotate the vectors so that they are all in 2 orthants. Okay, so it's not in 1 orthant, it's in 2 orthants. Okay. So we can rotate the vectors so they are all in 2 orthants. And now what we do is that we take the corresponding Gram matrices for the vectors in each orthant. Okay, so there are 2 orthants. We say the matrix Z1 is the matrix corresponding to the vectors in the first orthant, where the remaining vectors are replaced by 0. And we do the same for the second orthant. So we get these 2 matrices Z1 and Z2. Now, since all the vectors are in a single orthant, we know that these matrices Z1 and Z2 are completely positive. Okay. And since they are completely positive, we can apply Motzkin-Strauss inequality. So we get this bound right here for these 2 matrices. And to get the bound we want with 2 times the clique number, we simply combine these 2 inequalities. So here we have this inequality right here, which is basically Cauchy-Schwarz, if you want. And this inequality right here is because the matrix Z, all its entries are non-negative. Okay. So by using this procedure, we get the inequality we want. So we get that this right here holds, and from this we get all the way back to the inequality we want. Okay, which is this one. All right. So if you look at this procedure in the end, where we get this upper bound with a constant times the clique number, you can see that we can do this more generally. Okay. So for example, we can define what we call the bounded rank vector chromatic number, which is given by this program right here, where in the program for the vector chromatic number, we consider this extra condition right here on the rank. Okay. And well, we also know by the Motzkin-Strauss inequality that the clique number can be written in this way as the optimum of this program. Okay. So by what I told you about this fact that we can rotate the vectors and that doubly non-negative is equal to completely positive, when the rank is at most true, we get that this bounded rank vector chromatic number is actually equal to the clique number when D is 1 or 2. And in general, we can prove this inequality right here for this vector chromatic number, bounded rank vector chromatic number, okay, where when D is large. So some comments about this. As I told you before, the vector chromatic number can be computed in polynomial time, and it's known that it's hard to get a constant factor away from the clique number, okay? So in particular, this shows that when we add this restriction on the rank of the vector chromatic number, we get something that is hard to compute. Okay, it's hard to compute chi-vec D, but chi-vec is not hard to compute. Okay, so it's only because of this restriction on the rank that it's hard to compute. Yeah, so there is this, and well, there are examples showing that you cannot get the Bolobash-Nikiforov conjecture using only this program right here. So we have examples where, well, this doesn't hold in general. The clique number can be smaller than the chi-vec tree of the graph. And what we do in order to prove these two results with a better constant and this asymptotic result when the clique number is large, is that we consider other programs instead of this one, and we conjecture that these programs they can actually prove the conjecture at least when the clique number is large. Okay. So yeah, so this is what I had to say about the conjecture. So there are also some related questions. The first one is another conjecture by Elphik, Linz, and Vokschen. By the way, Elphik is going to talk at the algebraic graph theory seminar on Monday, so you're invited to attend. He's going to present some of his conjectures. Okay, so they conjectured that if you consider this sum of the squares of the eigenvalues of the graph, where now we don't go all the way up, we don't consider necessarily all the positive eigenvalues, maybe we just consider clique number of the graph of them, we can get the same bound. Okay, so this is stronger than the Bolobash-Nikiforov conjecture, and in this same and there is this result by Kumar and Tagada from 2024 where they actually they verify this conjecture right here when for graphs with few triangles. If you want to learn more about this conjecture or related conjectures, there is this excellent survey by Liu and Ming on solved problems in spectrograph graph theory, where they give a lot of results around these conjectures. And well, and there is this other conjecture by Elphik, Farber, Goldberg, and Vokschen, where they conjecture this upper bound for the sum of the squares of the positive eigenvalues of the graph when the graph is connected. So the bound now, it's of this form right here. It's 2 times the number of edges minus number of vertices minus 1. And you can see some partial results toward this conjecture in this article right here, positive and negative square energies of graphs. Okay, that's it. Yeah, thank you.